So I would like to introduce our third speaker, Henrik Wenzel. He is a professor at the University of Southern Denmark. I have heard Henrik's presentation before, and I'm sure he will pinpoint some of our biggest challenges going forward towards a green society. And I think he might surprise you about some of those challenges. Today he will focus on the global agenda. So let's give him a warm welcome to the stage. The floor is yours.
Thank you very much. My title was given as the global perspective, but it also includes what you could say the future of biogas and the competitiveness of biogas compared to other approaches in the green transition. So that's the frame of my talk. Let me very briefly first hold on to a few very important framework conditions for the competitiveness of biogas and for the reason that we are looking into a world with a lot of biogas. And one is the availability of biomass at a global scale. If we are to get rid of the fossil fuels, we need some other source of our carbon for our fuels and feedstocks for plastic, etc. And biomass is an obvious source. And we have various types of biomasses. But what you see here in this table are a number of studies that have been done internationally by a variety of organizations, including the Danish Climate Council, IPCC, the International Energy Agency, and other, of how much biomass do we see that we have available in the world for energy purposes. And that is energy and feedstock for plastics and other chemicals. And as you see, the studies become younger and younger, more and more recent. The estimates of how much biomass we have available is to some extent slightly falling. There was a very well-known study from 2011, 11 years ago, by an expert group under the IPCC that said somewhere between 100 and 300 exajoules. Denmark is using 0.7 exajoules, just for comparison. But these estimates have been falling towards now kind of 100 exajoules altogether in the world is the estimate. And how much is then 100 exajoules? I will show you in a second. But we could also translate it to per person, because this is all like by 2050, something like that. And by then we are just about 10 billion people in the world. You know, the 15th of November this year, we turned 8 billion in the world, and by then we will be around 10 billion. So it's easy to convert to per person, and that adds then up to 10 gigajoules per person or per capita per year by 2050. And how much is that? Well, that's just equal to around 600-700 kilograms of straw. So just around these two big bales of straw, that's 10 gigajoules. That's what you have per person for a whole year for everything you want to do that needs carbon, and if you can't use fossil fuels. The major part of this will be agricultural residues. Of course, you have both agricultural residues and forestry products and residues for this. But the forestry biomass will mainly go to buildings and paper industry. The thinnings and so on from forest industry goes a lot to paper and cardboard industry, and the timber part, of course, goes to buildings. And we become more and more people with higher and higher welfare, living standards, so we get more and more timber into our buildings. That is where the majority of the forest biomass will go. So the agricultural biomass, which is the biggest part, around 2/3 or something of these 100 exajoules, that is available for energy and material purposes. So let's look at how much is that then. This is a map of the world, and all the green parts is where we have agriculture. And if you look at how much does this agriculture produce as the end product, that is how much we eat, that can be translated, these calories we eat per person per day, that the whole population of the world is eating 3 gigajoules of energy equivalents in our food per day. So that's the end product of all the activity in this part of the world. The energy equivalent of our energy sector, including transport, is by 2015 was 77 gigajoules per person per day. And the International Agency and others predict that in a business as usual development scenario, we will look at something like 90 gigajoules per person per day by 2050. So that's 30 times more the energy equivalent of what we eat. That is what is a bit scary, because if we're going to go away from fossil fuels, looking at biomass as the potential substitute, I mean, and we even also need feedstocks for the plastic and other chemicals, which is not part of this number. And even converting biomass to fuels takes more energy loss than going from fossil fuels. So we are looking at somewhere 100, 110 gigajoules per person per year altogether. And we can't produce that from area. We can't produce it from biomass. We simply don't have area enough on the planet, and our biodiversity is already suffering. That is why we talk power to X. That is why we talk hydrogen. That is why we talk CO2 as another carbon source besides biomass. But biomass is attractive, and some biomass types are very attractive because, like manure, like straw, they are very feasible to go into biogas, for example, and what Bruno Sander called a fertilizer factory that will produce an attractive fertilizer for agriculture and take care of soil quality and all that, besides producing energy. And also biogas plants can reduce the climate impacts of agriculture at the same time. So, this is a picture that is a little bit academic. What you have, each of these dots, each and every one of the dots is a whole energy system design study. So how to create a fully renewable Danish energy system. And if you see one example here, so this dot represents a fully renewable energy system designed for Denmark by 2050. And what the location of the dot in this diagram shows is that in this specific energy system design, this specific study done by EnergyNet or the Energy Agency or some university, many actors went into doing these studies. This specific design shows that the whole fully renewable energy will need like 30 gigajoules per person per year of biomass, but it will also need like 7 gigajoules of hydrogen per person per year. So this specific actor designed an energy system that succeeded in being 100% renewable using 30 gigajoules of biomass and 7 gigajoules of hydrogen. And the rest was electrification, right? So a lot of battery cars and heat pumps and all that. So all of these dots represent such a study. And this is many man years of work going into this. But what it shows is that you can really depend a lot on biomass. But you remember the whole world had only 10 gigajoules available, and here you have some studies using 120 gigajoules per person to succeed with a renewable energy system. But then the studies become more and more electrified, so the system gets more and more electrification. Until a certain point, you can lower the biomass demand by electrification. But at some point, you can't do more. You have fully electrified your person transport on the road. Industry, 75% is electrified. Heat pumps in the heating sector, etc. Then you can't go any lower in biomass unless you have hydrogen. And our finding, this is a study of a PhD student of mine, we found here together that if you want to go as low as 10, which is what is globally available, gigajoules per person per year of biomass, you can't do it without having at least 17 gigajoules of hydrogen per person per year in the system. That is more than the biomass. So what you're looking at, if we are to succeed in a fully green system, fully renewable, we need more hydrogen than biomass, energy-wise. That's an interesting conclusion that has some relevance to biogas. This is the reason I show it. I'll explain what the relevance is. So, I've here taken a Danish system. It is a global point that I'm making, but I'm using the numbers from a Danish system because they're easier to understand. Here you see we have some biomasses available, bio-waste, manure, straw, and here you have the numbers of the quantities we have available in Denmark. Now it's in petajoules for the whole of the country per year. And then we have some wood here going into heat and power, and we have CO2, and we also have CO2 from the atmosphere, and we have solar and wind for our electricity. This is what we have. And this system here represents a full solution to a fully renewable energy system. What you don't see is the electrification part. You only see the parts of the system that needs carbon, which is a third of the whole system energy-wise. 2/3 we can electrify, 1/3 we need carbon. And here you have how much we need in the aviation sector, road transport, almost nothing, shipping, materials, plastic and other, and industry, and something for heat as a peak heat in the coldest winter day, and something to back up the electricity system. All together, that's our demands. And here you have our supplies. And if you, I'll go back, if I can, yeah. And part of this, biogas plays a key role, and I can explain further why it's such an elegant system integrator. I'll come back to that. But we produce methane. We take almost nothing from the soil, because on the long term, the soil carbon stays the same. And we take the methane and we store it, and we can take it up somewhere else at some other point in time, and we can produce fuels and plastics and what have you out of methane. And the technology to do that is already existing. Many places in the world, we are producing jet fuels and plastics, naphtha for plastic production, out of methane, where the methane only comes from the off gas from oil extraction. But the technology is there, and one of the key actors in the world is Shell. And today was the press announcement from Nature Energy that Shell has bought Nature Energy. So now the ability to use methane as a feedstock for jet fuel and for plastic comes closer to Denmark, because Shell is sitting on that technology. That's an interesting piece of news. So the point is, however, that we do not have here carbon enough. If you count how much carbon we need, or how much energy we need in carbon compounds on the demand side, it's like 40 gigajoules per person per year, and we have only 20 in Denmark. Globally, we have only 10, but in Denmark we have 20 because we have so much agriculture. We can even have more if we go towards more grass and clover grass, but that's today's situation. So we need something more. So we need CO2 and we need hydrogen produced by electrolysis that we can enter into the fuel production as well. However, all CO2 sources will become attractive, because at the end we need to capture CO2 directly from the atmosphere. According to my models, it's half of the CO2 that we need, at least. We need to get directly from the atmosphere because we don't have enough from point sources simply by 2050. So, therefore, all CO2 sources become attractive, and that's why we also are looking at, of course, using the CO2 in the biogas itself. That's 40% compared to 60% methane. So it's 2/3 of the carbon that you have in CO2. And if you upgrade that, you can boost your methane production by 2/3, that's 67%. And the extra investment is only like 5-10% extra. And you get 67% more methane. So that is, I'm convinced, going to happen. And we have worked with that for some years, 4 years now, in the lab. This is a lab-scale reactor where we use these microorganisms, archaea, that grow as a biofilm in our reactor, and we feed the reactor simply with gas, CO2 and hydrogen, and some methane is in there as an inert gas. It doesn't do anything. And then that is simply converted to more methane. And here is, again, an academic slide showing this is the length of the reactor and what is the production capacity when we start feeding the reactor with the gases in the top, and then going down centimeter by centimeter, we monitor the production capacity. And in the beginning, we're looking at just around 50 cubic meters of methane per cubic meter of reactor. And as we start using the hydrogen in the top of the reactor, of course, it is falling. But to compare, the methane production capacity of a conventional biogas plant is 1 cubic meter per cubic meter of reactor. So here we are sitting between 50 times higher capacity per cubic meter. So it's very, very area efficient. The footprint of it is very, very small. Right. And now we have been in pilot scale for 1.5 years well, and it has worked very, very well. honestly almost no problems. Of course, we learned a lot of how to feed the nutrients and how to do the trickling and remove the process heat and so on, because this is a heat developing process. But we know how to do it, and a demo scale plant is under construction now at Glansager Biogas Plant near Sønderborg, and the plan is that it's in operation July next year, and that it's going then into full scale. It's 1/3 of full scale, so it's practically full scale down there. And that's, as I see it, it's going to be the first full-scale Power-to-X plant in Denmark. And here's another academic slide, but it's very, very interesting for anybody who thinks of investing in biogas. What you have here is the time on the x-axis, and what you have up on the y-axis is the cost of methane production, and also the cost of other things. So here what you see is that the cost of wood chips will increase, because if we start demanding more and more wood chips, wood is a scarce resource, it's a limited resource, and the higher the demand, it's a natural demand supply development process, the higher the cost of supply, because the less competitive suppliers will come into the picture if demands are increasing. So that is increasing, and straw will probably follow that trend. Hydrogen, however, hydrogen cost is following an economy of scale and a learning curve type of development, and this is a cost projection by Bloomberg NEF, and they show that today the cost is just around here, 25 euros per gigajoule, but it will fall quite dramatically as they foresee it over time, and that is the cost of a Danish situation, where we're selling a bit of heat for district heating as well. But if you compare these, then the extra capex part of the methanation plant converting this hydrogen to methane is not a lot. And this is then the cost of the methane produced from this hydrogen. And before we know, the cost of producing methane from hydrogen and CO2 is getting lower than the cost of producing methane from straw. So by 2027, it is my prediction that electromethane produced from hydrogen and CO2 of the biogas is going to be cheaper to make than biomethane from straw. And that is interesting because any owner of a biogas facility of some significant scale at least will have a very strong incentive to start establishing this methanation technology on their facility, starting more or less already now, because in a few years, like 5 years, it is really competitive to do so. Right, and by the way, the horizontal red lines are the natural gas prices from when it was low to what it was last winter, and what you could buy it for in August on future prices, estimated by Green Power Denmark. So we can produce methane at half the price it was on average last winter from hydrogen and CO2 in a few years.
Is it only capex or is it capex OPEX?
This is capex and OPEX because this is the total levelized cost of hydrogen.
Okay.
And this is the extra capex of the methanation reactor.
Yeah, and OPEX.
Yes. Yes. Yes, it is.
Yeah, thank you.
Because capex and OPEX of the methanation reactor itself is almost nothing. Yeah. This is the total cost of production. Right. Furthermore, and now I'm ending, biogas is a pretty good system integrator, as also Torkild showed that using the biogas digestate for pyrolysis is interesting because it gets extra fuel out that biogas cannot take out itself. You could also use HTL, hydrothermal liquefaction, and then it gives even more hard degradable carbon back to the soil. Then you can take the syngas or the bio oil and make a fuel out of it, but that is a little bit difficult, so we are looking also into producing simply more methane out of the syngas because we know that these microorganisms can also convert the syngas to methane. And then you can use, of course, the methane for LNG to sail your ships or run your trucks, if you like, or you can produce methanol out of the raw biogas or out of the CO2. So there's a lot of options having this biogas as a backbone in the system. Final slide. To wrap up, the role of biogas and why biogas is an elegant technology in the future. It's the cheapest renewable hydrocarbon we can get. We know that. Biogas from manure is the most climate-friendly hydrocarbon because it's even carbon negative when you produce it from manure. It's the best system integrator because it's a good organic waste management option and valorization of organic waste. It creates a good fertilizer return to agriculture and an optimized redistribution of the fertilizer. It gives hard degradable carbon back to soil. It integrates hydrogen very well. We know that we need all this hydrogen integrated in the system. We also know that the vast majority of it we need reacted with carbon. And where do we get that CO2 from? Well, biogas is a really, really good place because it's the cheapest CO2 source. And the technology, as I showed, is probably the first to happen. And it's pretty simple to have these microorganisms do it for us. High technical readiness, and it's going to be the cheapest Power-to-X technology as well. It's mature and ready as a feedstock for both jet fuel and plastic, the methane pathway. And it gives a maximum uptake of hydrogen per carbon in CH4. Methane is storable in the gas grid. It is already distributed to industry. Gas turbines on biomethane or electromethane is the best and cheapest option to back up the wind. I mean, in terms of economy, you can forget about nuclear power as a backup for wind. It's way too expensive compared to a gas turbine. And it's the lowest investment also for peak load boilers for the heat sector. Thank you.
Thank you so much, Henrik. Are there any questions before we have the lunch break here at the biogas scene? Yeah.
Could you go back to the slide with the graphs concerning the capex opex? Yes, this one. So you are saying that in 2025, 6, 7, the process of e-methane from biogas CO2 will be lower than the straw technology.
Yeah.
So,
however, one thing is that, of course, we're using the CO2 from the raw biogas, so they are kind of linked.
Yes. Today we are putting it in the air.
Yeah.
Yeah. So this will be a thing to utilize it better in the existing traditional manure-based first generation conventional industrial biogas. This is the future.
Yes.
Okay, thank you very much.
But also, we have a lot of interested stakeholders from waste incineration. There's a big Finnish waste incineration plant that has contacted us and Biogas Clean, who delivers these plants, to take the CO2 from flue gas from waste incineration into a methanation filter. And we have also talked to Aalborg Portland on a non-binding way, but they are also interested.
So this is, we can continue building this on the manure and not necessarily look into the straw as one single input, as others also are working on.
My point is that when we get towards like 2030, all biogas facilities should do this.
Thank you.
Thank you. We have one more question.
Thank you for a very good presentation. For the Power-to-X, I think normally we always hear that the electricity for the electrolysis is going to be a hindrance, at least for quite, 10 years maybe, because it's so slow in getting up windmills. But will you also be able to get the electricity or is this basically going to stop the process for a while?
Sorry, the question was if we don't have enough green electricity
for the Power-to-X.
Yeah, that it is limited.
Yeah.
That's right. I mean, and there's a lot of discussion. Should we first use the green electricity for something else than Power-to-X, or what should we do? I'm doing more like a backcasting. If we are to meet our targets by 2050, if we are to meet our climate targets from the Paris Agreement, if we are to meet our national targets from our own government, we are to be fully renewable. We are to be carbon negative even beyond 2050. And the question is, how can we do that? And there is only one way. It's only green electricity is the only solution, because what else do we have? We can't use more area. It's really not an option. So biomass is not an option. So it's the only way. So we need that extra electricity. And we do have an Esbjerg declaration now saying 65 gigawatt in the North Sea and 7 times more in the Baltic Sea as well. That's 10 times more than today. And that's by 2030. So if we are just close to following that, or just half of that, we will have much more green electricity. But it's a precondition. You're completely right. But I don't think we should first use all the electricity for heat pumps and battery cars, because it's a bit more efficient climate-wise. And then when we've done that, we could go towards Power-to-X, because we need a decade or more, 2 decades, to roll out the Power-to-X, to get it implemented. And we need it implemented because there's a lot of integration issues here. Power-to-X produces a lot of heat. We need to integrate it in our heat sector and so on and so forth. We can't do it, in a discrete manner. It has to be co-optimized.
Thank you so much, Henrik. Now we'll have the lunch break here at the biogas scene, so I'll see you back at 1 o'clock, where we have Sten Bitsch from the Danish Biocommodities that will talk about the green grass protein.